And these drawings are far from perfect, but what's important is what the drawings say. It's not about the drawing itself. So now we've got how many triangles? For every 12th of the dodecagon, we have 1, 2 of these 15, 15, 150 triangles, so 15 degrees, 150 degrees, 15 degrees. And we've got 2 times 12, right? Of those, so that's 24, with side lengths S, 1, and S. And again, we don't care about S, it turns out in the end not to matter. And 1 times 12 of the 60, 60, 60, which is 12. Okay, well, now we've broken it into easy to deal with pieces. Now we've broken it into easy to deal with pieces, but we want a way to relate that back to the area of the square. Well, to do that, I'm going to use this angle. Since this side of the square is going to be a straight line, and we know that this is 60, and this is 15, and this is 15, and this is 60, we know that each of these angles, they're going to be evenly divided since these side lengths are equal, are going to be 60 plus 60 plus 15 plus 15, and we'll call this B, plus 2B equals 180. Well, this is 120, and this is 30, so we get that 150 plus 2B equals 180. And so B has to equal 15. Now that's interesting, because now we've got we've got an angle of 15 degrees right next to a side that's equal to the side of the dodecagon. So we can actually form another one of these triangles, because this has to be one that's the same as a radius, and this will also be the side length. We know that because of these triangles. And so we can do that, and now we have a triangle that's 3 side lengths, which is the same as this triangle. And we do that to each of the 4 corners. And now, to get the square, we've now added 2 times 8 of those triangles, which is equal to 32. And 2 times 4, excuse me, 8 total, 2 times 4, and 1 times 4 of those triangles, which is equal to 16. So now, we've got the square in terms of these triangles and the dodecagon in terms of these triangles. And we want the ratio of the dodecagon to the square. We just want the area of the dodecagon in terms of the square. So I'll show you how to get there in a minute. You divide this by the number of triangles in the dodecagon, and it turns out to be 4 over 3. And you divide this by the number of these triangles in the dodecagon, and that's also 4 over 3. This means, since these ratios are equal, it means the distribution of these triangles from the dodecagon to the square is equal to the distribution of these triangles from the dodecagon and the square. And Tommy will explain the rest to you.
Alright, so what does this mean? So, we have 32 of the isosceles triangles in the whole square, and 24 of them are in the dodecagon. So that means that the dodecagon has 3/4 of the isosceles triangles. So, and this also means if you look down here, 16 equilateral triangles total. 12 of them are in the dodecagon. So the dodecagon also has 3/4 of the equilateral triangles. So the dodecagon has 3/4 of the equilateral triangles, and it has 3/4 of the isosceles triangles. So what does that mean? That means if we look at the areas of the square and of the dodecagon has to have 3/4 of the whole area of this whole square here. But guess what? We already know the area of this whole square. It's right here. The area of the square is 4. So what does that tell us about the area of the dodecagon? Well, it's 3/4 of the area of the square. So it's equal to 3/4 of 4, which is 3. Which is exactly what Kurschak claimed over 100 years ago. So look what we did here. We started with a dodecagon inscribed in a circle. Pretty complicated. But what did we do? We broke it down. We were able to say, all right, well, instead of using the circle, we can make a square, which is much easier to deal with. And instead of dealing with this complicated dodecagon, we can break it up into triangles that are easy to deal with. Triangles that are equilateral and isosceles, that makes more sense to work with. And by doing that, we were just able to find a relationship between the area of the dodecagon and the square. And that was enough for us to arrive at our final answer. And that is Kurschak's theorem. Thank you for watching.